So the title says Mobile Crowdsourcing Socio-Physical Analytics, and they're two distinct things. So I'll just quickly start off by just giving a brief, not in really an introduction of myself, but more an overview of the work that I've been doing for the last 4, 5, 6 years. And when I look at it myself, I compartmentalize my work into actually 3 distinct bins. And so the left to right progression actually captures how long I've been doing this sort of work. So there's one piece of work that's about what I call mobile wearable IoT sensing, and the core idea behind that is that you want to capture the activities that people are doing in the physical world. So these could come from mobile devices, it could come from wearable devices such as smartwatch. We've done a lot of work around understanding, for example, what you're eating and how often you're eating, or if you go into a shopping mall, you know, which exact product you're interacting with, you know, sort of it involves localization of trying to understand which shelf you're interacting with, how high and up and down, and what gestures you're doing, et cetera, when you pick up an item and so on. So that's one category where we look at a mobile device or IoT devices, et cetera, as fundamentally sensors, and from these sensors we extract signals and we try to understand the physical activities that people are doing. And today's talk will actually not cover that topic at all. So the second piece of work is actually a piece of work on urban mobile crowdsourcing. So the fundamental idea is that you can take any urban environment, such as a campus, or you can take a city, and you have a bunch of tasks that you want humans to do around the city, and the tasks are pinned to specific locations. So these tasks could be check if, you know, the toilets in a particular campus building floor are clean or not, or if, you know, a certain pathway in a park has, you know, sort of it has potholes on it, or if there's vegetation that's not been cut, et cetera, et cetera. And the whole idea is how do you bring in human beings and how do you utilize them as agents to perform these tasks. Now, just at the outset, I think it's important to understand, whereas the first piece of work is, as Cecilia was characterizing, sort of mobile and a very systems flavor. The second piece of work, yes, it's systems, it's about building and laying things out in testing, but it's fundamentally about uncovering aspects of human behavior. So this is more of a behavioral understanding of, you know, what are the right incentives to give people, how do you make sure that they perform tasks, how do you ensure that, you know, we can give them the right recommendations about specific tasks they want to do while satisfying some of the privacy concerns that they may have, et cetera, so on. So that's second. And the last piece of work, which I will also talk about today, and in some ways it's the last 2 that have underpinned my visit to the Turing Institute. And this is work that in many places one calls a smart city understanding, or urban analytics and urban sensing. And in particular, we've been blessed at Singapore, as many of you may be aware of having access to a large trove of sort of digital data from government and public agencies. So we have access to data often in real time from, you know, every bus and every taxi and every parking garage, and, you know, video feeds from over 100 cameras and so on. And the whole idea there is to try to get an understanding of what events are happening in the city. In particular, my focus has been on understanding outlier events, because events by definition can be outliers because they attract people coming in, and they attract, you know, these people eventually have to disperse, and they leave sort of they ripple, you know, that the events has a footprint essentially on these various sensors, which could be the buses, the taxis, et cetera. And so that's the model that we're going after. So at a high level, you can think of this as an inverse estimation problem. We have all these observations from the buses, the taxis, and so on, and we're trying to uncover what events would have likely caused these perturbations. So that's, in a nutshell, sort of the high-level overview of the 3 areas that I work in. I'm also going to give you one slide overview on LiveLabs, which is a big research center that my colleague Rajesh and I have been running for the last 6 years now. And the reason this is not a talk about LiveLabs is just to give you an understanding of there's an immense underlying systems effort in building out a test bed, in collecting a pool of human subjects, in supporting things such as indoor location tracking, and all of these are enablers of the kinds of behavioral studies that we've been able to do, because without that underlying support system, you know, you'd have hypothetical questions, but you wouldn't have ways to actually test things out empirically. So what LiveLabs does, this has been again for 6 years, it's basically a testbed in multiple urban venues and public venues in Singapore. And what the testbed does, it has a pool of participants and it monitors their behavioral context. So this relates to the first part of my work, where I said you use mobile devices, you use the sensors on them, Wi-Fi based tracking, and you understand what they're doing, with whom they're interacting, et cetera, in these places, and you expose those context understanding through APIs or through interfaces that allow other people to run behavioral experiments on these people. So just as an illustration and just as a proof of concept of what LiveLabs can do, imagine, and our target for this is not computer scientists, it's actually behavioral scientists, marketers, people from the disciplines of business who don't necessarily understand all the nitty-gritty and intricate details of computing. So imagine you have a sales associate in some movie theater, running a movie theater, some movie theater manager, and he says, well, I want to do a targeted promotion strategy, and my targeting is I want to deliver a movie discount, but I only want to deliver it to the group of 4 or more people. So I basically want consumers who come in groups of 4 or more people, who stay in a coffee shop that may be right across and then the same floor as the shopping mall, and they stay in the shopping mall in this coffee shop for more than 10 minutes together. So only if they satisfy all this criteria, then when they're about to leave the coffee shop, that's when I want to give them this mobile coupon, this discount, and say what happens. I want to observe what happens. Do they redeem it? Does it increase the uptake rate, et cetera, et cetera. So it's sort of a behavioral experiment. And what they do, and I'm not going to go through the demo, et cetera, what they do is they go to a portal. So this is like any other behavioral portal. We have this running, it's live. So you can select your control group or your test group. You can say how many participants you need, what are the context triggers you need to satisfy A and B or C, et cetera, et cetera. And then they click deploy and run. And that's where we take over. So imagine we have a bunch of participants who come in and they go into the coffee shop. So we're capturing the data from their mobile devices, from their Wi-Fi interfaces, et cetera. And we deduce through our analytics that 4 people in a group are sitting for more than 10 minutes. So we know they're in the coffee shop. We have done group detection, which is a piece of work we've done. We know they're sitting as a group. We knew they were queuing. They bought the coffee. They sat down, et cetera. And afterwards, when they get up and leave, we know from their real-time location tracking that they just stepped out. So they satisfied the second part of the trigger, which says now we should actually do an intervention, which is push them a discount. And that's discount, again, we have a bunch of mechanisms, mostly through the mobile device, but it could be an in-app notification, an SMS, an email. You can think of all these possibilities that you do. So we push the movie discount to these people, and then the advantage is you continue to observe them, because then you can see, do they go actually redeem it? Do they afterwards go to dinner? Or do they go and take the bus and leave? So now you're giving a feedback loop to the marketer in this case and saying, oh, that strategy wasn't very successful. So why was it not successful? Okay, because these people eventually went for dinner, if I pushed this at 5 p.m. And then he might refine his strategy and say, oh, I want to do the same strategy, but I only want to do it for people between 8 and 10 p.m. at night, because that may be a better sort of subgroup who are more receptive to this particular discount. So that's the big picture vision. So this thing has been deployed, all this location analytics at SMU. Sentosa is a resort island in Singapore. Suntec is a big convention center where we actually had this live at the Mobicess conference last year. And at Singapore's National Museum. Now there's a huge deployment effort. I mean, you can understand this has been going on. We have a location corpus trace at all these places for over 24 months. At SMU, these have been running for over 3 years now, at least tracking 100,000 people longitudinally over time. So the various research components, okay, did come back, was, so we have some passive Wi-Fi based location tracking, group detection, behavioral experimentation portal, some things on building energy automation that have just been sort of rudimentarily started. So again, all of this was meant to give the background. So let me just jump into the 2 pieces that I'll talk about today. One is mobile crowdsourcing, which is about 3 years of work been going on. The socio-physical urban analytics, it's more recent. And the results in all of that are very much work in progress. I want to sort of caution that I don't have any sort of compelling, thing that we have established and proven over a long period of time. But I think what it will illustrate is, the possibilities around the rich data sets and the types of research questions we're asking. And at a very high level, to me, the research questions that I'm asking for these 2 specific areas is, so you have an urban platform to play with. You have a city, and the city has a lot of sensors, and they give you data. It could be water sensors, temperature sensors, sensors on buses. So in Singapore right now, there is an initiative going on that it has 130,000 lampposts, and over the next year, every lamppost will have a sensor board on it. So you can imagine the kind of rich data, infrastructural data you'll get from it. So to me, the question is, these sensors will reveal a bunch of things about the city. And the question is, how can we intelligently combine them with human-generated reports and actions? Because human beings, so one of the taglines I use is, Singapore's population, roughly about 5.5 million. So the government's making huge infrastructural deployments of sensors of various kinds, several billions of dollars. And you could complement that by 5.5 million sensors, 5.5 million mobile sensor nodes for free. These are people you might have to maybe incentivize them or maybe give them some feedback in terms of their city and their neighborhoods, but they would do these tasks for you and give you sort of annotated reports for free. And how can we best exploit them? And so, of course, along with that comes the question of, so the question is, how do you best combine these sources of urban data? So you have various types of sensors, and you have the human sensors, and they have many different characteristics. So human sensors are somewhat subjective, less reliable in certain ways. They're also more mobile and opportunistic. People will report only in certain cases. Physical sensors have calibration problems. We know that. Human sensors have subjective errors in terms of what they believe and what they say. So how do we combine these things? So that's the background. Let me move for the next 20 minutes or so into the area of mobile crowdsourcing. So within mobile crowdsourcing, we have done this work, and over a period of time, especially in large urban centers in Asia, we see a lot of opportunity for a lot of commercial services moving into this so-called, sharing economy, participatory economy, and so on. So the one that I'll briefly touch on that we're actually actively working on is package delivery. And this one is important because, so within Singapore, as e-commerce, et cetera, takes off, there is actually both B2C and B2B need to sort of ship small packages, like for example, some shoes from one branch of a shoe store to another branch of a shoe store. And you typically use courier services to do that. And the price points that were about $10 to ship like a package over, in the same day within the city have now dropped to about $1.50. And the way it has dropped is because these things have gone sort of the way of Uber, et cetera. So they're being crowdsourced. You put an app, you ask people who are passing by their way on a motorcycle or going in a train to pick it up and drop it off. So this is sort of crowdsourced based last mile logistics. There's a lot of work around municipal sort of sensing, municipal spot fixing, which is all sorts of so for example, I know for a fact in Singapore, you have a town council, and town council gives out contracts to vendors who say, oh, you have to go cut the grass, you have to mow certain places, you have to paint certain buildings, and after that, they have to pay a separate company go do the auditing, that did they do it on that particular day. And so our hypothesis is, why not just ask the residents to do this auditing? They pass by and say, either take a picture or just report, has this been cleaned today or not? And of course, with a lot of crowdsourcing, these are not full-time dedicated agents, so they're opportunistic. You usually try to do multiple authentication. So you'd ask multiple people to verify, do majority voting and so on. So there are similar examples. Another big thing is store compliance. So I didn't realize this was actually a pretty big business. So retail, large companies like Procter & Gamble and so on, so they run promotions with mom and pop retailers, 7-Eleven, big chain in Singapore. So every week they'll say, oh, you have to put our bag of chips on the top shelf next to the sales counter, et cetera. And they then need to send companies or dedicated agents to go and audit these places to say, are they complying or not, because they get special bonuses or commissions on it. So again, the idea is, why don't you just ask the shoppers when they go in to take a picture or report, and you would cut out sort of these needs for other types of dedicated agents. So what is the problem? So I'm setting up sort of the background. So the problem that when we started working on this about 4 years ago, we said, what is typically done in mobile crowdsourcing? You build an app, you roll it out, it has a bunch of tasks, and essentially the agents are completely free. They pull out the thing. At most, they do a proximity-based search. They say, what tasks are near me? And they pick tasks that they choose to and that they want to do. So it's opportunistic. Now, the travel patterns of people are non-deterministic. So we don't exactly know if I give you a task to check on the garbage bin over there, will anybody else come into this room afterwards and be willing to do this? So we have uncertainty in sort of the availability of the supply pool. Now the tasks themselves could be of two kinds, and that has a little bit algorithmic difference in sort of the approaches. So one is a single location task, which means you go report. So if I ask you is this garbage bin full or not, you have to come here, check the garbage bin and leave. Whereas the package delivery tasks have both a source and a destination. I have to pick up this bag from here and I have to drop it off at the reception. So I essentially have to go to two locations. So our the three problems that we identified were, one is the lack of coordination. So fundamentally, this is sort of like a tragedy of the commons, right? If all of us are free to choose any task we want, there'll be natural skews because we might all end up bidding for the same task, et cetera. So it just intuitively seems, and there are many well-known problems that have been documented with these platforms, that if the decision making of who was to do which task was done in a centralized manner, taking into account the movement patterns of different people, you would do better because you'd be able to more equitably distribute the tasks among people and while minimizing their sort of overheads and detour. Then there was also a lot of work has been done on the right incentives, how to bundle tasks together. My feeling was that a lot of it has not been empirically tested to see how humans react. So there's a lot of work, for example, on pricing that looks at auction-based or game theoretic models of how agents would bid for prices and set floors. And that would work in autonomous agent-based systems, but not necessarily with human-based systems because we don't necessarily follow those models. And finally, a problem that is open and that we continue to work on is people often accept tasks and forget to do them. There is a belief that you have to remind people at the right time. So this is like one of the core pieces of context-aware computing. To engage people and get them to be receptive and actually complete the task, they have to be reminded at the right time and the right instant. And how do we do that? Taking into account all the uncertainties with the mobile sensing technology. So in a nutshell, and I won't cover all of these today for obvious reasons, we've been working on the crowd logistics piece with a local company on how to bundle tasks which are pickup and delivery tasks. We've been doing a lot of work on this experimental mobile crowdsourcing on our campus, using our campus as a test bed to try out different crowdsourcing strategies. And we are just poised with Singapore's Municipal Services Office, so it's basically a government arm, to launch this nationwide. So this is supposed to go out in September or October. The app's all laid out. This will be thousands of regular citizens doing tasks across the city. And so we want to see how successful our mechanisms are in the real world. Just maybe one of two slides with any kind of math on it, and I'll skip the math as well, but just to give you a flavor. So what is the difference? So our basic model is this. So we started off by saying the centralized crowdsourcing could be looked as a variant of the classic orienteering problem. So an orienteering problem is, or classic orienteering is this. I have an origin-destination pair. I have a bunch of tasks. I go from O to D. And I have a total travel time budget. So I cannot go to all the tasks. So I find within that budget how many tasks can I fit. So I get a certain reward. Now the variation that we have is if you think of mobile crowdsourcing, first you have multiple agents. And essentially our idea is that I'm going to go, I already have a routine path. I'm going to get up from here, take a train, change a bus, and go to a certain part of London. So that's my routine path. And what I'm trying to do is I will give you an additional detour budget. So this is how much I'll deviate from my routine path, and I want to get the maximum reward within that detour budget. So if you look at it that way, so this is one origin-destination pair that goes this way. So normally it would go OMD, but he's additionally doing task 8. And theoretically, if you're a pedestrian, you're doing it for 0 additional cost because it falls in your path. Whereas O2, D2 is a different agent, and that person normally would have gone this way, but now they're going this way. So they're detouring. They're picking up more rewards, et cetera. So the overall objective function, if you think about it, again, let's skip the math, is I want to maximize the reward in expectation. So the way we model this is that there are multiple agents. Each one of them have multiple possible paths. Each one has a probability assigned to it. So in the expectation, I want to maximize across all agents the amount of tasks they do given a certain detour constraint. So The constraint is that their detour cannot exceed either a certain percentage of their normal travel time or a fixed amount, say no more than 5 minutes of additional detour. So within that, how many tasks can I pack across everybody? So you can solve these problems, again, sort of a classic Lagrangian relaxation version of it. You can break it up into 2 sub-problems, and they sort of work in iterative fashion. One, for each agent, you assign it a set of tasks, and then given a certain assignment, you find the best routing through those tasks. And eventually, you will, you can use sort of a gradient, subgradient descent algorithm to solve this technique. Now, what do we get out of it? And again, I'm just going to leave very high level because the details matter. You're welcome to come talk to me afterwards. So the dark line is our approach, including something called local swap. So you're basically not just doing gradient descent, you're doing some randomization in between. And this data is actually taken from what's called MRT. So it's the commuting data set of millions of commuters in Singapore. So we found on average that they have, we leave out the people who are traveling salesmen. These are your plumbers, electricians, et cetera. They don't have fixed routines. But people who go commute to work, we found on average they have 1.92 routes or 2 routes. So there could be a bus this way or a train and bus the other way, et cetera. Now, in general, if you apply this technique, and in this case, the tasks are synthetically generated and distributed across the city, you can get more tasks completed. So as you see, as the detour threshold increases, the percentage of tasks that are completed eventually approaches 100%. So if you allow 15% additional travel time in what you normally anticipate, the group of people can cover almost all tasks within the city. And the more important thing is, because we are centrally coordinating this, the average detour for one person is actually lower. So overall, you're improving productivity. No surprises there. Now, the question is against what? So against is the system where each individual sort of non-deterministically picks out their app and says, I want to see what tasks are closest to me now, and I will do a certain number of those tasks. So essentially, taking a longer time horizon, accommodating the uncertainty that people have, will still allow you to do better task assignment and task performance. Now, so with this theoretical background, we said, what do we do? So why don't we try testing it with a test bed somewhere? So we went back to the fact that we had LiveLabs means that on our campus, we had the location traces of pretty much every occupant. And with that, we said, why don't we build up a real crowdsourcing platform, and we're going to give people tasks to do, and we're going to reward them with micropayments. And one of the sort of tasks they do is like the smart campus type tasks. And what you see illustrated here, eventually we build this smart campus type platform where you can see these are different levels these are different restrooms at different levels, and every 15 minutes we get reports. How clean is this? Which one needs fixing, et cetera. And so we actually have this operational for the last 4 years. So in general, on any one semester, we have about 8,000 total undergrad students. We have about 1,200 students who are part of this platform. They do about 50 to 60,000 tasks over a 10, 12-week semester. We leave out the finals week and midterm week, et cetera. So it's also an experimental platform where we can study different strategies, and we've rolled out the app and so on. So let's go look at some results, just some selective results. So one of the things that is well known in micropayment type task systems is, like we said, each task, in delivering task, for example, in package tasks, there's a payment for $1.20 or $1.50. Now, if you think of a city like London, if you say I'm going to pay £1.50 to deliver a task, probably nobody's going to do it. So the way most people get around is by amortizing the travel cost by bundling. So you say, okay, here are 5 tasks. They're all in the vicinity, and you'll get £7.50 or £7.50 if you do all the tasks. So then the reward quantum goes up. People are willing to do the task. So we came up with this bundling strategy, and then we said, what is the outcome of bundling versus non-bundling? Now, we also said we have A/B. So in A/B, what it means is we have people to whom we recommend tasks using our algorithms. The other group, we just open up. This is like classic crowdsourcing. You just show them all the tasks. They're free to do what they want. So we found that push users, these are the people whom we proactively recommend tasks. They're still free to do what they want. They are more than 2 times productive. So how do we measure productive? Productive is the dollars earned per detour minute. So we know we actually track their movement paths. We see what are their stay points and where do they deviate. And we say, oh, this is how much detour they had to take to perform the task. So it turns out that by bundling tasks, people prefer bundling tasks, and it improves their overall productivity. And 80% of the users include, this is the detour distribution, incur detour less than 15 minutes over a semester. So this is 5 days a week, say roughly 8 weeks, so that's 40 weeks. So in general, we found, again, this is of course as a very urban campus, it's centralized, etc. But they were able to do lots of tasks that just happened to lie along their paths or just required minimum detour, 30 seconds this way, do a task, come back. So it seems like a very feasible scheme, and that bundling is actually quite effective. The other thing that we did, and this one I'll skip because the result is very easy to understand, the analysis is not so important. We found in any campus, there are popular areas of campus, less traversed areas of campus. So there is a skew in the performance of tasks. So this is the flat task pricing. So if you do the flat task pricing, so you can see that there is a skew, that there are some places that see a lot of tasks being performed, some don't, in terms of the percentage of total tasks that were defined there. So the whole idea is, why not do differential pricing? And so we found out that the simplest and most effective mechanism, so we compared a whole bunch of theoretical mechanisms, is just do inversely proportional to the population density of that place. And that reduced the skew and improved the courtesy of the distribution by a 5-fold factor in terms of reducing the variations among the different completion rates across the campus. So again, this sort of reveals a very simple pricing strategy that you do even when you sort of extrapolate it across neighborhoods and so on. And the last slide, the second last slide on this, and then I'll stop talking about the collaborative crowdsourcing piece. To me, this particular work was actually quite interesting because what we found is, of the 100 tasks that were recommended to people and that were accepted, about 80 or 82 of those tasks were actually being completed. So about 18% of tasks were actually accepted and not done. And when we went back and investigated, we found the reason it was is because people would accept a task in anticipation that they would go by that place. But then their plans would change. And when their plans changed, they didn't go there, they didn't complete the task. And of course, that's bad for us. So we came up with this idea. We said, well, if you accept the task, and it's a bundle of 4 tasks, let's say. And remember, the definition of a bundle is that if you don't do all 4, you get paid zilch. You get paid 0. So you have to do all 4. Now, if you do 3 tasks and you say, oh, the last task is very far, I can't get there, why not offload that task to your friend, to your buddy? And the hypothesis is the buddy might be close by there. You use whatever, WhatsApp or whatever mechanism, and offload. If that person performs the task, you guys split the reward. So you benefit because you don't lose out on all that money, and the other person is sort of doing you a favor. So that was the hypothesis. Then we evaluated the strength of ties on the campus, etc., and we found this phenomena. So this axis is the physical tie strength. It shows sort of the closeness between any 2 pairs of actors or agents in the system. And this is the task completion scores at different locations. And we found, you can see that they're very positively correlated. No surprise. What does it effectively mean? What it means is that your close friends are likely to be in the same areas where you are. In a campus, this is not surprising because some of your closest friends will be in your cohort. They'll be in your, in your school, in your year. You guys will probably have the same schedules, etc. So our basic hypothesis that if you are somewhere and your friend might be somewhere else turns out to be false. They are more often than not also in the same place as you. However, it turns out that it improved the completion rate by 14%. And we wanted to know how did that happen. So this mechanism was actually quite effective. We went from 82% to 96% completion rate. So it turns out that the way you explain this is first by observing these 2 graphs. This is the nominator. This means these are people who offloaded the tasks, who basically requested a buddy to do the task. And you can see that before we started the referral scheme, this is the x-axis. This is their task completion rate after task completion detour after they started the referral scheme. So you can see that there are people in this category and people in this category. What do they mean? That there were basically two groups of users. One group was, I will only do tasks that are 5 minutes away, means within the same building. I'm not going to go out of my way at all. And there are people who will go out of their way and do tasks. This is just two groups of people. And both of these, the tasks that they referred to are very far from them. So there was always, this part of our hypothesis was true. You always offload a task that you're very far from, 3 buildings away. What happens with the nominees, which is the people who accept the tasks and do them? So again, they were in 2 categories, detour sensitive and detour insensitive. These are the detours they encounter when they do their regular task. But for all the offloaded tasks, they all experience very high detours. So it turns out that the nominees are willing to go out of their way. It's not that they're close by when a task gets offloaded. They just are willing to go out of the way because a friend or a buddy asked them to do it. So as opposed to a platform asking them to do it and giving them the reward, if a friend asks them, they're more willing to do it. So this is sort of a behavioral nudging aspect that we uncovered that I think is very interesting and that we hope to use in our subsequent national level trials as well. I want to talk about one slide on user privacy. It's again based on this empirical data. This is actually unpublished work, so it's still sort of being refined right now. So all of this proactive crowdsourcing, it works great. We've shown it works, but what's the cost? The cost is you need to tell the system as a worker, you need to give your entire path trajectory, right? Because it's only then it can do the matchmaking. So this has a privacy concern. Now, we wanted an approach where basically I am an agent. I will do the obfuscation completely on my phone. I am not coordinating with any global system. There is no trusted third party, which is often an assumption in a lot of privacy systems. So I am just going to observe my own history, and I'm going to perturb my locations and send them out. And I yet want the benefit of getting recommendations that more or less align with my path. Is this possible or not? So there were 2 approaches investigated. The simpler approach, which I won't talk about much, is called entropy-driven modification. So essentially, you just build your own profile. You see the places where you stay the most amount of time. And these are usually your office or home and stuff. And these are places that you say the lower, they are low entropy locations for you, and you're most sensitive about them because you don't want them revealed. Whereas high entropy locations, this hypothesis is places you visit very rarely or not at all, you are less likely to be concerned about revealing them. So this is the simple approach. The more complex approach, which is the randomized response, borrowing the technique of randomized response, it works as follows. So I'm just giving you the overview. So I look at my location, I get a collection of locations, and I try to see which locations are very popular. So think of bus stations, taxi stands, train stations, etc. These are generally public locations, so I should be less sensitive about sharing my information at there. And I also try to see which locations have low entropy for me. In other words, I spend a lot of time in them. So there are 2 aspects of sensitivity. One is they're public versus private locations. The other is that I end up spending a lot of time on them. So I try to incorporate both. Now the question is, how do I get public versus private, because I want to obfuscate all my location. So that's where we borrow from randomized response, and I say I'm going to tell you my location with a certain probability, and I'm also going to tell you a bunch of other random locations nearby with a well-known probability. Because of the properties of randomized response, if everybody does that, the server doesn't know who is where, but it can reconstruct the statistics of the popularity of locations, and it can feed that back to you. So this is sort of a completely private way of exchanging information between a server that doesn't know its location but can reconstruct overall aggregate statistics, and then each individual agent is making its own decisions on what to reveal. The end result of all of this is this graph. So if you look at this, there's a Q parameter, and this is very standard. So we basically allow this as a tuning knob between sensitivity to your own, the entropy of each location in aggregate versus what it means to you, and how much detour. So I could choose to say, I'm not here, I'm at St. Pancras, very public location, but then I have to see what the cost is. Compared to me, what is the detour, the distance to that location I'm revealing. So I want to do a trade-off and balance between the 2. So in general, if I choose Q higher, I am saying I'm going to give you worse and worse locations, but I'm going to stay more private. If I make Q 0, I don't care privacy. I'm just going to give you locations that are close to me, that are true mine. And as you vary Q, you can see what is happening, that the detour obviously keeps going up. On the other hand, the number of tasks completed. So we actually looked, because I'm giving you a false report of my location, the crowdsourcing system in return is unable to give me the best matches of tasks. So I'll end up getting tasks I can't do. So we find that we get about, when we get to about 30% additional detour, I have, the percentage of tasks completed can drop from 90% to about 80, 75%. So on average, I am improving my privacy attribute super linearly, and I am losing a little bit in my ability to perform tasks. So that's the trade-off that we've been exploring and that we're implementing now in the national pilot that we talked about. So here's the national pilot. So the national pilot is, we're taking the crowdsourced application. We have something called OneSource, which is like NYC 311. People just upload complaints, and we're converting it into a proactive mechanism. So you have citizens who are given tasks, and what is very interesting is through work of my colleagues, how are those tasks being generated? The tasks themselves are being mined from social media. So people who post on Twitter, I passed by, oh, this place was stinking, or said, oh, I felt dark in this neighborhood, it was not safe. So we're actually doing that sensing and creating tasks and giving it to people saying, hey, are you passing by that area? Is it really unsafe? Are the lights working, et cetera? And so this feedback loop will allow us to build a more proactive national scale monitoring system. That's the vision we have for this piece of work. I'm going to skip the smart notification in the interest of time. I'm skipping the crowds bundling work as well. The main thing with the bundling work that I wanted to say, we've achieved some success, is this. So we don't know the paths that workers will take, but you have to create bundles ahead of time. And the way we do that is every day we take the OD flows across the MRT station. So we have an aggregate traffic matrix, and we basically create bundles that best align with those overall flows. Because our assumption is on any given day, the random set of workers who choose to do tasks where their statistics will closely match the traffic flow statistics observed in aggregate. And therefore, if you do a better match, so if there are a lot of people who come from the east end of London to King's Cross, and if that's a very heavily traveled path, I should bundle tasks that follow that route. So it doesn't matter who on a particular day ends up doing the task, it's a good chance that we will match with them. So that's the work that's been going on there. We've been getting some good results. So in the next 10 minutes, I'll just focus on the socio-physical urban analytics portion of the talk, because as I said, this is more speculative, more advanced, but I wanted to share the vision of what we're after. So what we're after is we think of all these sensors as probes. So you have the infrastructure sensors, GPS of taxis. This has been very common, very heavily analyzed. You have mobile sensors. People participating can give you, sound, environmental quality, all of these things. You have social sensing. People post things on Twitter. People take Instagram pictures, et cetera. What we are after is I call anomaly detection. So we look at the pattern of the city, and I am going after small-scale events. So my eventual goal, which we're nowhere close to achieving, is suppose today a neighborhood school has a concert the school ends at 3:30, and then there's a parent-teachers conference today from 3:30 to 4:30. So my hope is that I'll be able to go down to that microscopic event, be able to isolate and say there was something happening there today. Why would that likely to be captured? Because my hope is normally I see a lot of people, the occupancy of the bus shoot up at 3:30. Today that's going to get time shifted to 4:30. I see some parking garages there empty out at 3:30. The parking garages should now get filled up around 3:30 because a lot of parents come in, and then they'll leave later on at 4:30. So there are some deviations from the norm, and my hope is that first we do capture the neighborhood where these deviations are happening. Then I go to social media and try to explain or annotate what this is. So if there were a lot of people posting there, oh, my child did a great concert today or whatever, then I can potentially explain that this is what happened in that neighborhood. This is sort of the big picture vision. Now, I'm not going to go through all of these. They are all different pieces of the work. So one is to detect anomalous events, understand their evolution. But I think for today's talk, I'll talk a little bit about this ongoing thing on multimodal sensor fusion. I will talk about detecting anomalous events and one thing that we found on our campus. This is not urban, but well, actually it also uses the MRT, the data set from the commuters. The main message that I wanted to say there was that social relationships often explain events or help detecting events that aggregate statistics do not. Now, what is the first and overall framework that we have constructed? So you can think of social feeds, and this is work a lot of people have been doing. This is not our work. You have to look at relevancy, you have to look at credibility, you do topic detection. What we are bringing in is let's start at the pipeline of urban informatics data. So far, our work has looked as first get measures of occupancy. Now, for each type of sensor, occupancy means different things. I'll cover that very shortly. Then you model norm. This is a very standard supervised classifier and outlier detection scheme. So you see what is the norm on any given day in a particular time bucket at a particular location, and then you look for deviations from the norm. Once you identify the deviations, you pass here. You pass these geotagged topics detected here, and that's where you both localize an event and you try to do an event exploration. This is the sort of the two-stage pipeline that the overall framework has right now. So let's just do detect anomalous events. So think of like a campus. I mean, many of you professors, you're in campuses, and you said there are events. So some events are very high intensity. So if you have Wi-Fi data, the classic thing you can detect is fire drills. You can detect convocations and commencements, because all of a sudden there'll be a huge influx or a rapid drop in the occupancy of a particular space. Those are easy to detect. But then there are some low intensity events. Now, this is not a low intensity event, but what I wanted to say there is, so in our own work, we realized that people were setting up little ice cream stands to give away free ice cream as part of like some religious cultural organization. So that means on our student commons, there were 4 people standing there, and the flow of traffic going by was not really that different. But how do you detect such an event? The fact that 4 people are standing by is not that unusual. So this is sort of the background on it. So I go back to LiveLabs, so where we had this observation over a period of time, and we extracted a bunch of features. Let me just again sort of at a high level explain the features we are extracting. So the first is we look at the Wi-Fi location traces, the localized traces. We can extract the physical movement of people. That gives us occupancy features. You can take this room and say in every 15-minute bin how many people are here. Just total number of people present. That's typical occupancy features. And there are variations of that. You can look at is the occupancy going up, going down. You can sort of do deltas on it. You can look at the rate at which occupancy is changing. You can look at the stay time of people in that duration. But these are all basically derived from physical location. What I wanted to talk about was there were a few other features that we derived, and we derived this purely from the location data itself. So these are the social interaction features and network features. So we constructed these pairwise tie strength between people, and we also looked at whether people are alone and in groups using our group detection. So this is more a shorter term indication of social interaction. Tie strength is something built up over time. How closely am I related to you? So what do we do with, so here are some examples. Again, I'm just selecting a few, the details I'm obviously skipping over. How do we infer tie strength? So one thing is what I call spatial precision. So suppose you and I are in this room and there are 8 people present versus you and I are in a meeting room where just 2 of us are present. I'm going to give more weightage to our tie strength to this because here I'm dividing it across the 9 people. So in similar way, we had temporal precision. We also had so temporal precision means do I meet you every day of the week versus do I meet you 6 times today. So each of these are indicators of either short, intense interactions or sort of continuous interactions over time. Now, there are many other variations that one can do on it, including the longevity of the relationship. One thing we found very useful, again, this is very specific to a campus. So it turns out, in terms of defining strengths, there are certain places where if you go as 2 or 3 people, they are very good indicators of tie strength. So one of them was the gym. So somehow in a university setting, if you go in with a workout buddy, that friend is really a close friend of yours. And the other place was a library. In a library, again, this is all on our campus, we found that if you're there with just one other person, that person is kind of closely related to you. Whereas if you're there with a group of 3, 4 people, which is typically what you do with projects, that's a very weak indicator of a relationship, because those are more transactional interactions that people have. So anyway, that's the data from the Wi-Fi system. So we had about 1,700 LiveLabs participants. But we also had data of the tap-in, tap-out over the, the public subway system of Singapore. And you do the same analogous thing. You see, when people are commuting together, are they going into locations? So I usually come into work here from the west side. But today, if I happen to go to Parliament, then there's high likelihood there's an event that I'm going for, because it's an unusual anomaly in my pattern. So you can analyze public records like this as well. And here are the various features that we extracted. So one is the occupancy features, the transition and dwell time. So the fact that I made a transition today from the Turing to Parliament is unusual, because I never go there. So it must be indicative of an event that I'm going for, a very soft indicator. And finally, the groups and tie strengths. And what is the end result? The end result is, with all of these features, I get, so we had curated a bunch of events. So we have a precision of about 50%, a recall of about 65% on these events. So first of all, they don't look like very high numbers, especially for people from the world of machine learning. But a lot of these events that we looked at are actually very low intensity events, because we had to look at an event database. As I said, this was like a taekwondo club holding a practice session in our public concourse, where there were like 6 members of the club and hundreds of other people coming. The reason we were able to isolate those is because of the social strengthing. So there are 6 people in this room. There may not be an event going on, because whatever. But if it turns out that all these 6 people always go to the gym together and always go to eat together, the fact that they're here today cannot be just a coincidence. They're here for a common purpose. And that's the thing we're exploiting, that the fact that people are socially tied, have strong ties, and they happen to be in same places together is significant. That's one of the lessons we learned. So I'm going to skip over the piece on image relevancy as well. And I'll talk about this ongoing piece of work on multimodal sensor fusion. So what is the belief here? So the belief here is, okay, this is the Singapore Grand Prix. If you don't know, it's supposedly the world's only nighttime public road race. The reason it's kind of controversial is because the race day is on 18 September every year around that time. But all the roads in the downtown area are actually closed 2 days before and the day after. And they start doing roadblocks 3, 4 days after. So it does cause a lot of inconvenience to people in that neighborhood. And so it generates enough passion around it. So the question is, can we start detecting events like this from the various things that we have? And the questions that I wanted to, I'll pick one thing today, are the different modalities. So I'm observing, what is my data? I have bus data, I have taxi data, I have traffic camera data. Can I identify what is the specific event? What are the micro events? Because even though the roads are closed, there is a race, there's a pre-race event. How can I isolate these things? So the data set that we have access to, here are some examples. So we actually have data from 70 cameras along that way. We get, these are not video, you get an image anywhere between 1 to 15 minutes. From that we can extract the congestion level. Actually somebody is working to extract the composition of the cars. There's a lot of buses coming in, a lot of taxis, etc. The bus service, there are over 5,000 bus stops. You get the occupancy level of the bus and the GPS level, GPS location of the bus once every minute. So it's actually pretty fine-grained along all the different bus routes. Then you get social sensors as well. So these are the 21, this is over that 5-day period, 21 million posts in Singapore over that 5-day period. Geo-coordinated posts, obviously much, much lower. The number of posts with one of the keywords related to the Grand Prix, even lower, but those are what we were using. Now, the approach is, what happened here? Okay, so one of the things we found out is different sensors have different precision and recallability. So what this graph is showing is this 0 point, this axis, this is the epicenter of the event. as you're moving out from the epicenter, away and away, this is the recall. So recall here means that things were perturbed for 6 days. We know that. So if you have a recall of 1 means that all those 6 days, that particular sensor said that it was anomalous. If a recall of 0.5, it picked only 3 out of those 6 days. So what you can see is that on neighboring streets, for example, this is based on just taxi data, you have pretty high recall because either some roads are closed or there is unusual demand of taxis on that road, so you can figure those things out. Whereas if you go, for example, to tweets, so tweets you can get a reasonably good recall only on the days of the event, not before or after, because there is no difference in understanding what people are doing. So the multimodal sensor, this is actually the active work going on. The belief is this, there's 2 hypotheses. So we have an event happening at the center, and we think that it sort of dissipates. The perturbation dissipates out from the center. So you'll have the highest standard deviation right close to the center, and as you move away from it, now of course you have to take into account the connectivity structure of the streets. For example, buses only go in one direction and in opposite directions. And the other is the more connected 2 regions are, the more correlated that behavior. So if certain streets are connected or certain streets, this is a predecessor street of me with a lot of flow, then the fact that a lot of people get on the bus there, we should have a lot of people on the bus here too. So I should be able to discount that. So the end result that we have, I want to leave you with this last chart. Again, the same thing. This is where the epicenter of the event is. And we look at the deviation, the local outlier factor score for each region. And we see that right now, it seems to follow this drop-off pattern. So what we are hoping to do is to be able, after we establish this, is go into the inverse estimation problem. Because once you begin to see a pattern of this, then you say what is the center place that would best explain. It's like a maximum likelihood estimation of what is in space and time the event likely to be most centered at. So I'm going to conclude. I'm going to skip this as well. I'm just going to conclude with this last chart. I think moving forward, I think especially for those of you who are potential collaborators, et cetera, in mobile crowdsourcing, we are also looking into the issue of, so far we've been very operational about, improving the city, bus, dirt, cleanliness of, tax garbage bins, et cetera. There is actually a huge push to say that why not use community and opportunistic crowdsourcing to do community support services, especially for the elderly in the estates. Somebody takes them to the doctor, somebody takes them to the grocery store, buys the groceries for them. And one very interesting thing happening in Singapore is saying, if you do this, it will actually give you virtual microcurrency. You can use that to then hire a tutor for your child. So it's really going back to like a barter system, but using a community-based virtual currency. On the urban detection, I said one of the big opportunities is around these 130,000 lampposts, and we'll have data from them in hopefully about 6 to 9 months. They'll have there's still talk going on what exact sensor they'll have, but it includes short-range radar, actually IR sensors. One of the very interesting use cases for this is they're going to use Bluetooth beacons as a potential neighborhood GPS, because they're all on fixed locations with very short range. So you can park your UAV, et cetera, very precisely using BLE beacons. I think that's a very interesting data set that will come up. And the key takeaways I wanted to say is, like many other cities, but Singapore is pretty far advanced. There's a lot of public data sets, and continuously the government is updating them. And I think the combination of urban sensing with the mobile crowdsourcing is the way towards a future smart city. So thank you very much.